Welcome back. We're going to start today with a question. Can drinking soda kill you? And the answer is, technically yes, right? Because there's long-term effects from drinking sugary drinks and things like that. But I really mean in like the short term. What should happen when you drink a soda to the pH level in your body, right? We know that soda is somewhat acidic, so let's go ahead and figure it out. So the volume of the human body in water, if you just kind of take the water out of our bodies, roughly 40 or so liters. So we're going to use that value. The pH of Coke Classic is about 2.53. So we're going to take a standard can of soda, which is a 355 milliliter can of soda, 0.355 liters. And we're going to take the acid from there and put it into our body and see what should happen to the pH in our body. So the pH of Coke Classic 10 is 2.53, which means the concentration of H plus is 10 to the minus 2.53, which is 2.95 times 10 to the minus third molar. So that's what we're drinking in terms of concentration of H plus when we drink Coke, and we're drinking 355 milliliters of that and diluting it to a total volume of 40 liters. That's just an M1V1 equals M2 V2 problem. I can't get my numbers right here. M1V1 equals M2 V2. And so our beginning volume is our 0.355 liters, and we have 2.95 times 10 to the minus third molar, and we're diluting that to 40 liters, and we're trying to find out the new concentration. And if you do that work, you get that M2 is 2.62 times 10 to the minus fifth molar. So, we diluted it into 40 liters. It lowered its concentration by a factor of 2 orders of magnitude. And then if you check the pH there, that is a pH of 4.58. Right? So technically what should happen when we drink a soda is if that soda and the acid in it is kind of distributed through our body, we should lower the pH in our body to about 4.58, assuming we started off relatively neutral. Now I'm going to tell you that the pH range in which you can survive, and it varies depending on who you ask, but it's not too far off, the 7.35 to 7.45 range. So if drinking soda should get us down to 4.58, we should all be dead every time we drink a soda, or even apple juice. Apple juice is acidic too. We should die by drinking apple juice. Why don't we die when we drink apple juice? I mean, it's a good thing, right, that we don't die when we drink apple juice. In fact, if you do the calculation, to get below 7.35 pH, even if you start at the 7.45, you should only be able to drink 3 drops, like drip, drip, drip of Coke before you die. I mean, really, that's nothing, because these pH changes are so large because there's a lot of acid in this. So what is happening inside our bodies that allows us to drink a Coke? And some people get like the big giant 7-Eleven super giant enormous gulp thing. And I had a friend in college who would drink this giant enormous thing 3 or 4 times a day of Mountain Dew every day. How come he wasn't dead when he did that? So let's look at what happens inside our body. Inside our body we have our little lovely red blood cells, and the pH in our bloodstream again needs to be about 7.35 to 7.45. So what has to happen in our body in order that we can drink an acid and not die? Well, if we want to drink an acid and not die, we need something in our body, right? If we're adding a bunch of H+, we need something in our body that's going to react with that H+. Now, of course, there's sodium hydroxide, right? We've titrated and things like that. But having a store of sodium hydroxide in your body, not so good. We talked about how sodium hydroxide dissolves organic matter, and we're made of organic matter, so not the best thing to have stored in your body. So one of the things our body does is it has a bunch of weak acid conjugates on hand. So you got A minus, right? Remember, that's our generic thing. It could be acetates, it could be phosphates, it could be whatever. But an A minus that can absorb that H plus, right? You can get H plus A minus makes HA, right? So you can get that chemical reaction in there. So our body has a bunch of A minus in here, and that will help absorb the H plus, any excess acid that we have. So that's great. So you can have a bunch of this on hand, which will help manage the pH when you add an H+. But here's an interesting thing. What happens if you have some, I don't know, basic something? Let's say you take a teaspoonful of sodium bicarbonate, and people do that. They'll actually use that as a health food kind of thing. I think it tastes really gross, but you know, I've heard of people doing that. Are they going to die because that's slightly basic? Well, if you want to have something to counter basic on hand, what do you need? If you're going to be putting a bunch of base into your body, you need to have something on hand to counter that. Now, of course, there is our gastric juices, which are relatively acidic, and so those can counter it all by themselves. But it turns out another way to do that, and it comes kind of naturally from what we did before, is to have a bunch of HA around. And then the HA can react with the OH minus to form water and A minus. Let me scroll that there. Okay, so we can have these two different things, right? So we can have some A minus around, we can have some HA around, and that helps us absorb small amounts of acid and base without changing pH very much. And you're like, how is that not changing pH? Well, look, what happens? I put this H+ in here, and then all of a sudden it reacts, and it disappears, and there's no extra H+ in solution. Since pH is just directly a function of the concentration of H+, if we absorbed 100% of our H+ forming HA, then we didn't change our pH at all. Same thing down here. We added some OH, right? And we know that although pH is not directly related to OH, OH is related to H+, so OH is related to pH. But all of it reacted with my HA to form water and A minus, and so we didn't necessarily affect the pH of our solution at all here either. But what do we want to do? We don't want to just protect from acids. We don't want to just protect from bases. We want to protect from both acids and bases. So guess what we do? We have both things in our body. Our body consists of a bunch of solutions where we have weak acids and their conjugates. Now, what those weak acids and conjugates are vary depending on where you are in the body. In the bloodstream, it's related to carbonic acid, right? So you breathe in, you breathe out carbon dioxide, and part of that is managing this HA and A minus in your bloodstream. It's really cool. So what do we call this? Well, we call a solution that has both a weak acid, right? That's our HA, and its conjugate base, right? That is our A minus there. And remember, we don't get A minus directly. We might have sodium partnered with our A minus or something like that. And that's how it gets into there. A weak acid and its conjugate base, we call that a buffer. And a buffer is simply a solution that resists changes to pH. Changes to pH. And then some people will add on addition of a small acid or a small amount of acid or base. Okay, so when we add acid, it reacts with our A minus and takes the acid out. When we add base, it reacts with our HA and takes the base out. So that is a buffer, and our body is made up of a bunch of buffers that are made and designed to regulate the pH very, very narrowly, 7.35 to 7.45. It's a very, very narrow range, and yet we can do that by having both a weak acid and its conjugate. Now, just to remind you, a weak acid and its conjugate, let's say we did have H2CO3. The conjugate to that is HCO3 minus. The conjugate is not CO3 2 minus. Conjugates are always the loss or gain of a single proton. So these two are conjugates. And these two are conjugates. But these two are not conjugates because there's a loss of 2 protons in there, and conjugates are always loss or gain of a single proton. All right. So that is what a buffer is. And we're going to look at all sorts of different kinds of buffers in this chapter to see what we can do to them. How do they maintain pH? How much can they maintain pH? And all sorts of interesting things. So here's a question for you. Which of the following is a buffer? So you remember what we just said in the last slide, what was needed to form a buffer? And then you're going to look at this list and try to decide which one of these fits that description. All right, go. What do you think? Okay, what do we need? We need a weak acid and its conjugate. All right, HCl, strong acid, H3PO4. Well, we know that's on our list of weak acids because it's not on our list of strong acids. And Na2HPO4, you're like, hey, that looks pretty promising. I've got a weak acid, and I've got the salt of it, right? Isn't that the conjugate? That's pretty promising, but it's always good to look through the entire list, right, just to make sure. We've got HNO2, and you'll notice one thing. I'm ignoring the concentrations. Okay, I'm ignoring the concentrations. As long as we have a reasonable amount of each one of them, and we'll look at detail of what's reasonable later on as we continue working on this. But as long as we have a reasonable amount of each of them, it doesn't really matter what the concentrations are, except for calculating actual pH, but just determining is it a buffer or is it not a buffer, the concentrations aren't too important. HNO2, that's on our list of weak acids, right? HNO3 is a strong acid, but HNO2 is a weak acid. KNO2, that's interesting. It also looks like it might be a conjugate. Potassium hydroxide, potassium iodide, no, that's a strong base, and it's not even a conjugate of each other, so we're good. So we've got either H3PO4 and HPO4 2-, or we've got HNO2 and NO2-. Again, how did I know these minuses? Because I remember my solubility rules that all sodium salts are soluble, all potassium salts are soluble. So I know they're going to fall apart into their ions. You have to keep that in mind. Don't look at potassium nitrate. You can't do anything with potassium nitrate. For one, because it doesn't exist. But for two, we don't know what is potassium nitrate in relation to HNO2. It's not its conjugate. It's not anything. But in solution, you just get the nitrate ion, or the nitrite ion, I should say, sorry. The nitrite ion. All right, so which is it? Is it number one? I guess we can use our letters here. Is it B or is it C? Hopefully, as you're looking across this, you say, hey, Professor Clements, H3 to H1, that's a loss of 2 protons. That's not a conjugate, right? And it's not. And so we're left with C, which is a weak acid, HNO2, and its conjugate base, NO2-, would be a buffer solution. All right, let's go ahead and calculate the pH of a buffer solution. So we're going to make a solution that is 0.500 molar HC2H3O2. Remember, that's acetic acid, and people often abbreviate that just to make their life easier, HAC, which I'm going to do. And then 0.500 molar NaAC, right? We've got sodium acetate. Remember, in solution, what that's going to form is AC- and the positive ion sodium. The Ka value for acetic acid, I'm just going to give it to you, but you should know how to look those up, especially in the tables that I give you, the ones that you'll find on Canvas. It's from the Tro textbook. I really like those tables. They're organized very well. So HAC, how are we going to figure out this equilibrium? Ooh, it's equilibrium. What do we do when we have an equilibrium? We do ice tables. All right, so let's do an ice table. We've got HC2H3O2, right? How do we also know that? Right, we had a K, right? If you have a K, big K, right? You have an equilibrium. So we've got HC2H3O2 going to H plus and AC minus. Let me go ahead and use my AC notation here. HAC. What do we have? Well, in our initial concentrations, before we were just saying, hey, we've just got some acid, we're good. But now we've got some acid and some base. We've got 0.500 molar of this. We do have some of this from the water, but let's ignore it for now and see what happens. 0.500 molar of that. All right, what's going to be our change? Which way is this going to go? Well, if we assume that the H is 0, then it's got to go to the right. So we're going to get positive there. We're going to get minus here, 0.500 minus x, x, 0.500 plus x. And we substitute that into our k expression. Ka is h plus ac minus over hac is x, 0.500 plus x, 0.500 minus x, and that's equal to our k value, 1.8 times 10 to the minus fifth. 10 to the minus fifth versus 10 to the minus 1, 4 orders of magnitude. That's a great time to try these small x assumptions. So we're going to go ahead and do that. Small x there. And we get that 1.8 times 10 to the minus fifth is x times 0.500 over 0.500. These guys cancel. And we just get that x is 1.8 times 10 to the minus fifth. All right, that was pretty easy. That's our H plus concentration. And so our pH is going to be the negative log of that, which is 4.74. So we get a slightly acidic solution here when we mix HAC and AC minus just using our ice table. Right? But the nice thing is, and we'll find this as we continue on, that this solution is going to maintain pH very well. So even if we add a little bit of acid, even if we add a little bit of base, the pH isn't going to change all that much. And we'll explore that in one of our future videos. Thanks so much for listening. Have a wonderful day.